My name's Gomulkiewicz, and I'm going to be talking about this painting. But before I do that, I want to make sure I mention my two collaborators on this project, Steve Krohn and Chris Ramin from the University of Idaho. For further details about what I'm going to be talking about, you can maybe take a look at this paper that just appeared in Evolutionary Applications. So, evolutionary rescue is an area that looks at conditions under which evolution can prevent populations from going extinct. And a necessary but not sufficient condition for the possibility of a population persisting in a harsh environment is that birth rates need to exceed death rates, or the intrinsic rate of increase has to be positive. So these are a number of replicate runs of a stochastic population model where the intrinsic rate of growth is positive, and certainly there's a lot of replicates that persist all the way through, but we see there's some unfortunate replicates that even though the growth rate is expected to be positive, nevertheless go extinct. And certainly in the case where intrinsic rates of growth are negative, there's a 100% chance of going extinct. So one of the questions I want to address is the opposite of evolutionary rescue. Namely, how does adaptive evolution affect the time that these populations go extinct, okay? So this is also a very practical importance in empirical studies of evolutionary rescue. So this is showing some data from a recent paper by Ruth Hofbauer and her collaborators where they put tribolium replicate populations on suboptimal diets that included corn flour. And without going into details, they did a number of manipulations, and they followed the population dynamics of these different tribolium populations, and they found that many of them were able to adapt sufficiently to persist through the course of the experiment. Some of them didn't persist and went extinct. But the point I want to emphasize here is that these studies, which were really quite difficult, only went for 6 generations. Evolutionary rescue refers to eternity, eternal life, right? So the question is, one of the questions that you might ask empirically is, are these replicates that haven't gone extinct by the time my money ran out for doing my experiment, are they going to go extinct a little bit later, right? So we need some information about the duration of populations in cases where they're going extinct. And in fact, this was pointed out by Guillaume Martin and colleagues in a recent paper where they pointed out that measuring the probability of evolutionary rescue in experiments is not that straightforward because of this time element. So in order to take a look at this general issue as well as this practical issue, what we did is we tried to determine, our goal is to determine the distribution of time to extinction for evolving populations. What is that? And then we use that distribution to look at how it depends on genetic diversity as well as abundances, and finally looked at the issue, the question of how does adaptive evolution affect the longevity of populations that are headed to extinction. Okay, so nobody's going to survive this, but how does evolution affect how long it takes to go extinct? So in order to look at this, we developed a biologically simplistic but mathematically tractable model based on clonal organisms. Okay, we had a number of clones, and we followed their densities over time. Okay, so each clone at continuous time, we assume that their dynamics were described by something called a continuous branching diffusion. Okay, and each genotype was characterized by an intrinsic rate of growth, that's a per capita expected number of offspring, and also what's called a reproductive variance, the variation in reproduction. Okay, so what you get then is a system that's described by this stochastic differential equation. So if you're not familiar with it, and a lot of us aren't, I hardly am, but this is basically your standard a density-independent exponential growth model, but it's got uncertainty in the reproduction. Okay, so this model has been around for a long time. It's been used by ecologists like Feller studied this or introduced this back in the 1950s. It's been used by MacArthur and Wilson in studying demographic stochasticity. It's been used in population genetics by, for example, John Gillespie in the 70s when he was looking at bet hedging. So this has been around for quite a while. I'm putting it to use in a maybe different context. So in order to set the stage for how evolution affects time to extinction in genetically variable and evolving populations, I just want to go over some of the basic features of the dynamics in populations that can't evolve. Okay, so let's look at what happens in genetically uniform or monomorphic populations. So I'll focus then on a population that consists of a genotype that just has this intrinsic rate of growth low r and this variance in reproduction v. And Feller showed back in the mid-50s, that's the 1950s, that the probability of extinction in any time t is given by this expression here. The x, by the way, is the initial density. Now this is a branching process, so each individual essentially reproduces independently of one another. And this form emphasizes that. This function f here, I'm going to call the genotypic risk function. It gives the probability of extinction of a single per capita individual at time t, and you take that and you raise it to the number of individuals of that genotype. Okay? So it's got this form here, and that we can use that to do a number of things. For example, calculate the mean time to extinction as a function of these parameters. So that's what this figure is showing. Each of these curves corresponds to the mean time to extinction for different intrinsic rates of growth, including negative to positive. And what you can see is that in each of these cases, which correspond to different initial densities or different variability in reproduction, is that the time to extinction on average goes to infinity as r goes to 0. And that's basically because when r is positive, there's a non-zero chance of eternal life. And so if you take the average of infinity with any finite number, the average is infinity. Of course, I mentioned that it's not, so this inset shows the probability of extinction as a function of the same range of r's, and you can see that as r gets positive, there is a non-zero probability of persisting forever, but those realizations that go extinct have a mean time to extinction that's given by a mirror image of populations with negative growth rate. So this is kind of a bizarre feature of this particular continuous branching process model that I'm looking at, but it makes it hard to ask what's the effect of a mutation that might move a population that's growing at 10% decline per time unit to one that's positive because of the infinity. So instead of looking at the mean, we used Feller's distribution to look at the percentiles of the time to extinction. And that's what this figure is showing. Each one of these curves is showing, this is the first quartile time to extinction, the 75% percentile, and then the black curve here is the median time to extinction. These are insensitive to these realizations that persist forever, right? And of course, I just put the mean in there just for comparison, okay? So I'm going to focus for the rest of the talk on these, mostly the median time to extinction. Of course, the other thing I want to point out is this genotypic risk function is in essence a measure of fitness or adaptation in the context of extinction. And that changes over time. It depends on these parameters, the R and V that I talked about. But this is a way to measure what I'll call maladaptation when we're talking about how adaptation, or adaptive evolution contributes to longevity. Oh, one other thing I forgot to mention back here. So let's look at, this is the median time to extinction as a function of the intrinsic rate of increase going negative to positive. So let's think about this thought experiment. These are monomorphic populations. The time to extinction is about 10 generations, or maybe 15. if suddenly every individual in that population were to spontaneously mutate to a growth rate of 0, that's a 10% increase spontaneously, the time to extinction would only advance by about 5 or 6 time units. That's nothing, right? It's very little. And so that suggests that maybe evolution does not have a great impact on how long it takes populations to go extinct. So I'm going to skip this in the interest of time, but if you're interested in adaptive surfaces, then maybe I can sell you on maladaptive surfaces in this, the opposite of evolutionary rescue world that I'm talking about today. Okay, so basically these genotypic risk functions let you compare different genotypes, including ones that have combinations of intrinsic growth rate and reproductive variance with the same probability of extinction at different times. It's time dependent though, and so what that means, for example, this is showing these genotypic risk functions over time for 2 different genotypes. One has a growth rate of 5% and a variance of 0.254. You can see that early on, that has a lower probability of extinction than the other one, but later it has a higher probability of extinction. So the problem with these adaptive surfaces is that they don't allow a permanent ranking of different genotypes because it's time dependent. All right, so what about evolution? So far I've just been comparing different genotypes, thinking about these monomorphic populations, but I would really want to follow genetically variable populations that can evolve, and so the way you use this continuous branching process framework is to use the independence to basically multiply these extinction risk functions for all the different genotypes raised to the densities. With this formulation, I'm not going to go beyond this, you can answer some questions. So for example, how does the appearance of a single spontaneous mutation in a population change its median time to extinction? So if you look at the left panel here, I'm showing the change in the growth rate that this single mutation induces. If it's to the left here, negative, it lowers the growth rate, or it could increase the growth rate. So if you look at the dotted line here, this is the ancestral population growth rate. It's a 5% growth rate, and the solid line corresponds to an ancestral state of stationarity, 0 growth, and then the thick dotted line is a declining population. So what you can see is that whether the effect of the mutation is greatest in populations with the highest growth rates, and it's least in populations that are in the harshest environments that are declining. So in contrast to conventional wisdom, which often characterizes selection as being more effective in harsher environments, with the question of extinction time, it's just the opposite. And you get a similar picture if the mutations are in the reproductive variance. One last thing I'll show you is what about sudden abrupt environmental changes? And so instead of mutation, just introducing one individual, what if all genotypes are affected in a polymorphic population by a change in environment, good to the right or bad to the left? And you get a similar picture. If the initial average rate of growth is positive, then the effect of the environmental change is either positive or negative much more severely than in populations with 0 or negative growth rate. So, to conclude here, what we've developed here is a process-based framework for predicting time to extinction of evolving populations that can be useful in a lot of applied biology areas, including medicine and agriculture. This framework emphasizes the importance of abundances and genetic diversity separately, okay? And finally, I'll just say that our results so far suggest that adaptive evolution has very little effect on the time to extinction for populations that are doomed to that fate. So thanks a lot for your attention.